So today we're going to learn about isotopes. Now recall that the atomic number from the previous couple lessons we've been learning about atomic numbers, the atomic number, this right here on neon, right, that's how many protons that an atom has in its nucleus. And we said that all atoms of neon in the entire universe, they have to have 10 protons. The neon's atomic number is 10, they must have 10 protons. However, that is not the case for the neutrons in a nucleus. Remember, the neutrons are also in the nucleus and they have a charge of 0, and they can vary a little bit from atom to atom and it will still be the same element. So neon can have different numbers of neutrons in its nucleus and it will still be neon. Now these different types of neon atoms are called isotopes. That's the definition of an isotope. Is an atom of the same element that only differ in the number of neutrons that they have in their nucleus. So remember, if we have our nucleus here, let's say this is our nucleus, and actually I want to do it a little bit bigger than that. So let's say this is our nucleus, right, of neon. We have, I'll do P for proton. Little protons in here. There should be 10 of them. I'm not going to draw all 10. There's not going to be enough room. And then we have neutrons, right? We have neutrons in here. So here's our neutrons in our nucleus. And this is not the correct numbers. This is just me drawing some in there so we can see that they're both in the nucleus. So we can talk about some examples of elements that have different isotopes. And if we look to the right, neon is actually one of them. And naturally occurring, there's 3 different isotopes of neon. We have Ne20, Ne21, and Ne22. And notice this is, if you went through the lesson, which you should have done already, you'll see on the left-hand side above the symbol is just a number, and that refers to the number of neutrons that that refers to the atomic mass that that particular atom will have. Because remember, the atomic mass of an atom is the number of protons plus the number of neutrons. So if we look at this neon atom, neon-20, we know it has 10 protons because neon always has 10 protons. That's its atomic number. And we know protons plus neutrons will give the atomic mass, and if the atomic mass is 20, we know it must have 10 neutrons in this one. I'm just going to put neutrons. If we look at the next one, we have 21. This is neon-21, so its atomic mass would be 21. We still have 10 protons, because neon always has 10 protons. But now the atomic mass is 21, so 10 plus what will give 21? We need 10 plus 11, so it must have 11 neutrons. I'm not going to write out neutrons. We know that that's neutrons. 11 neutrons. I'm trying to draw the quotation marks. 11 neutrons. And I'm not going to write it out there. I think you guys can know. So neutrons. Now we look at neon-22, we have an atomic mass of 22 with this atom of neon. We know still there's 10 protons, but it has an atomic mass of 22. So 10 plus what equals 22? We would have 12 neutrons in this neon atom. So these would be the different, what we call isotopes of neon. Right? They're all still neon, they just have a different number of neutrons. So naturally occurring, there's 3 isotopes of neon. Now, in the laboratory, scientists can create other isotopes of neons. I think your lesson says there's something like 16 different isotopes of neon that have been created in the laboratory by scientists, but these are the 3 that you would find in nature. So now you might be asking, well, Mr. Shell, neon, I thought, look at its atomic mass on the periodic table, says it's 20.180, and some of them have even, weirder numbers than that. It's because not all isotopes in nature are of the same abundance. So, if you look at all the neon that we can find, they're not equal amounts of neon 20, 21, and 22. They're different percentages of each in nature. And if we look here, the atomic mass on the periodic table is an average of all the naturally occurring isotopes of an element. So as it turns out, if we know the different abundances of the different isotopes in nature, then we can calculate the atomic mass. And so we can calculate the atomic mass of neon if we know the different abundances of all the different isotopes. So this is the average atomic mass. We say atomic mass a lot of times, but really we mean the average atomic mass. It's the average of atomic masses of all the naturally occurring isotopes in nature. And so we can do a couple examples of this right now. Let's say we have neon 20 again, and these are just going to be made up numbers, so if this isn't real. Let's say we have 50%, and then neon 21, maybe we have 40%. And neon 22, let's say we have 7%. Oops, this is a 53, sorry, 53%. So to calculate the average atomic mass, if we know the percent abundances and we know the atomic mass of each isotope, then it's easy to do. So we can say the mass, they abbreviate it mass. Okay, it's just the mass of N. Pen is not being very cooperative today. Mass of Ne, mass of neon, the average atomic mass of neon, is just going to equal the abundance, the percent abundance of each isotope times the mass of each isotope. So we have to take all three, so we'll do neon 20 first. We have its abundance is 53%. Now remember, whenever you're doing percentages in equations, you need to turn it into the decimal form. So 53%, you don't write 53, you write 0.53. That's 53% in decimal form. Times the atomic mass. And so generally the atomic mass, if we did the true atomic mass of neon 20, and most of them, they're a little bit less than exactly 20, so it would be like 19.98 or something like that. And remember, these are just made up numbers, but this is an example of how you would solve a problem like this. And then you just add all of those together for however many isotopes there are. So we have 3 this time, so we need to do 3 of them. We did neon 20, now we're going to do neon 21. So there's 40% neon 21, 0.4, that's 40% in decimal form, times 21. So times the atomic mass of neon, of isotope neon 21, and maybe, like I said, it's not exactly normally, maybe this is like 9 plus neon 22 is 7%, so 0.07 times 22, so 21.97. And so if we solve that problem, we would get 20.52 as the average atomic mass for neon. Now the true average atomic mass, we can see it here, is 20.18, and that's because these abundances are not accurate. I just made those up. But if you had the accurate abundances, you could plug it into this equation and then you would get 20.18. And you can do this for any element where you have the percents and the atomic mass of each isotope. You could do this for. And then one last thing I want to mention, the units, which I should have put here, AMU, standing for atomic mass units, and that was just calculated by it's 1/12 the weight of a carbon-12 atom. So you don't necessarily need to know how much an AMU is, you just need to know that atomic masses, the average atomic masses, and any atomic mass of an isotope will be in AMUs, atomic mass units.